The universe is a clock, but unlike any clock ever imagined, its hands do not trace an endless circle. They move forward, outward, inexorably, toward what we call the future. And if traced backward, they do not reveal an infinite history. They halt, suddenly, at a boundary, a beginning. A moment when the clock itself was first wound. 13.8 billion years ago, the universe emerged in fire. A singular moment we call the Big Bang, when time and space were born together in a single breath. From that instant, galaxies would rise, stars would ignite, and life would one day gaze upward to wonder at its own origins. Yet the mystery deepens when the question is turned backward. If time began with the Big Bang, what existed before? The paradox is almost unbearable. To ask what came before presupposes that time already flowed, that a before could even exist. But at the moment of creation, the river of time itself may have sprung into being. It is a silence before sound, a darkness before light, an emptiness before being, a place where even the word before collapses into meaninglessness. And yet the human mind cannot resist the question, if the universe had a beginning, does that not suggest a cause? If the clock of time was wound, who or what wound? This is the riddle at the edge of all knowledge, the boundary where physics falters, where mathematics dissolves into infinities, and where imagination dares to wander. A question not just of cosmology, but of existence itself. What lies beyond the beginning of time? At the dawn of the 20th century, time was thought to be absolute, steady, and universal. The ticking of a clock in one place was believed to be no different than in another. Space was seen as an endless, unmoving stage upon which the drama of the cosmos unfolded. But in 1915, Albert Einstein shattered this ancient illusion. With the general theory of relativity, he revealed that space and time are not separate entities, but threads of a single fabric, space-time, flexible, curved, and alive with the weight of mass and energy. The universe was no longer a silent void. It was dynamic, restless, shaped by gravity's invisible hand. And though Einstein himself believed the cosmos to be eternal and unchanging, his own equations whispered a different story. They hinted at instability, at a universe that might be moving, stretching, evolving. That whisper became a roar in 1929, when Edwin Hubble turned his telescope toward the distant galaxies. What he saw was astonishing. The galaxies were not fixed jewels in the night, but drifting apart, receding from one another like sparks scattered from a fire. The farther they lay, the faster they fled. The cosmos itself was expanding, carrying worlds away on a tide of space. If expansion was real, then the past carried with it an inevitable conclusion. Rewind the cosmic film, and every galaxy, every star, every atom must converge. The universe, once vast, must collapse into a single point, a singularity of unimaginable density. A beginning. It was Georges Lemaitre, a Belgian priest and physicist, who dared to frame this vision in bold new words. He called it the primeval atom, a seed of creation, exploding outward to form all that exists. It was a universe with a birth, a beginning written into its very structure. But such an idea was troubling. For centuries, science had resisted the notion of a sudden creation, fearing its echoes of theology. Many clung instead to the dream of an eternal cosmos, unchanging, infinite, without origin. Yet the evidence mounted, and with it arose the question that haunts cosmology still. If the universe began, what lay beyond its beginning? Here, at the very first articulation of a cosmic dawn, the paradox was born. To say the universe had a start is to imply a before. But how can there be a before when time itself begins with the event? This tension, woven into the origins of discovery, would shadow every step of science that followed. The revelation of an expanding universe did not arrive in silence. It struck the scientific world like a discordant note in a familiar symphony, a sound too strange to accept, too disruptive to ignore. To many, the notion that the universe had a beginning felt less like discovery and more like intrusion, as though an ancient philosophical door had been forced open. The comfort of an eternal cosmos, infinite in both directions of time, had been an anchor to rational thought for centuries. Now that anchor seemed to drift. Among those most resistant was the English astronomer, Fred Hoyle, a brilliant figure with a sharp mind and sharper tongue. Hoyle despised the very idea of a universe born in fire. To him, such a concept smacked of theology, echoing creation myths that science had long sought to escape. On a radio broadcast in 1949, he mocked the notion as a Big Bang. The name, intended as ridicule, would outlive him, attaching itself forever to the greatest scientific theory of origins. Hoyle preferred a different vision, the steady-state model, in which the universe had no beginning and no end. As space expanded, he proposed, matter spontaneously formed, filling the gaps, preserving the eternal order. For many, it was a comforting compromise, a universe that changed but never truly began. Yet the mathematics of relativity resisted such comfort. Einstein himself had once inserted a cosmological constant into his equations to preserve the illusion of stability, a term designed to counteract the pull of gravity and hold the universe still. When Hubble's discovery reached him, Einstein admitted the deception with rare humility, calling it the greatest blunder of his career. The evidence could not be ignored. The galaxies were receding, the fabric of space-time was stretching, the universe was alive with expansion. But if expansion were real, it carried with it a philosophical weight far heavier than the equations that described it. A universe with a beginning raised a question of cause, of a moment before, of forces or realities beyond the boundary of known time. Scientists found themselves caught in a paradox. They could measure galaxies racing outward. They could calculate the age of the cosmos. They could trace its history backward toward a singular moment. But when they reached that first instant, language failed. What did it mean for time to begin? If the river of time had a source, what lay on the far shore? It was in these early decades that the paradox fully crystallized. The expanding universe was not merely an astronomical curiosity. It was a profound shift in how humanity understood reality. A beginning was not just a scientific problem, it was a philosophical wound, a crack in the illusion of permanence, an invitation to stare into a realm where even thought itself falters. This resistance, this unease, would shape the path of cosmology for generations to come. The revelation of a universe in motion was not greeted with harmony. It entered the scientific world like a storm breaking over calm waters, scattering certainty, and unsettling the minds of those who had built their careers upon the idea of permanence. The notion that the cosmos itself had once emerged from a singular point was met not with celebration, but with skepticism, unease, and in some quarters, outright hostility. For centuries, the eternal universe had been a comforting assumption, a background that required no beginning, no cause, no troubling metaphysics. Stars might live and die, galaxies might shift and collide, but the stage itself was infinite, timeless, unchanging. To imagine instead that the universe had a birth was to trespass dangerously close to myth, to creation stories, to questions of origins that science had tried to liberate itself from. A cosmic beginning was not just a scientific claim. It was a philosophical intrusion. Among the most vocal skeptics was Fred Hoyle, a man of immense intellect and formidable wit. To him, the suggestion that the entire cosmos had exploded out of nothing was absurd, a flight of fancy unbecoming of serious science. In a 1949 radio broadcast, he mocked the concept with two dismissive words, the Big Bang. He intended the phrase as ridicule, a caricature of a theory he believed crude and naive. Yet irony would see the insult endure, becoming the very name of the theory that grew stronger with every observation. Hoyle championed instead a vision of an eternal cosmos, the steady-state model, where the universe expanded, yes, but without origin or end. Matter, he argued, must be continuously created from the fabric of space, ensuring that the density of the cosmos remained constant forever. It was an elegant refuge, a way to keep the universe timeless, infinite, untroubled by beginnings. Einstein, too, resisted the idea of a dynamic universe. His equations had revealed the possibility of expansion, but he could not bring himself to accept it. To preserve stability, he had inserted an additional term, the cosmological constant, a mathematical counterweight to gravity. It was an attempt to balance the universe on a knife's edge, holding it fixed in place, but the discovery of galactic recession shattered this illusion. Galaxies were not fixed jewels. They were fleeing on currents of expanding space-time. Confronted with Hubble's data, Einstein set aside his constant and conceded what his own mathematics had foretold. Privately, he admitted that clinging to a static cosmos had been the greatest blunder of his career. But the scientific unease did not fade with Einstein's admission, for if the universe were truly expanding from a singular moment, it raised a question more troubling than any equation. What does it mean for time itself to have a beginning? If the cosmic clock starts at zero, what came before the first tick? Could there even be a before when time itself had not yet unfolded? This was the fracture line between observation and meaning, between data and philosophy. Telescopes could chart the galaxies, equations could trace their trajectories, but neither could answer the deeper paradox. The expanding universe forced science to confront a boundary, a wall of mystery at the edge of time. And standing before it, even the most brilliant minds struggled with the same haunting thought. If time had a birth, what lies beyond its horizon? In the decades that followed Hubble's discovery, the scientific community began its first serious attempts to peer into the depths of the universe's origin. The expansion of space could no longer be denied, and the question of a beginning pressed closer. Yet with every calculation came a disturbing truth. Mathematics pointed backward to a singularity, a point of infinite density and zero volume where the known laws of physics dissolved. This was not a description of reality, but a breakdown, a place where equations ceased to function and understanding collapsed into mystery. Physicists wrestled with the singularity like sailors confronting a maelstrom, circling around it, probing its edges, yet never able to descend into its core. Einstein's relativity was the guiding star of this exploration, but it carried its own limitations. The theory was a magnificent lens for describing the large-scale universe, the movement of galaxies, the curvature of space-time under gravity's hand. But it was silent on the quantum world, where particles flickered in uncertainty, and probability ruled. Pushing relativity back to the birth of the cosmos, created infinities that could not be reconciled. It was as if the universe itself were warning that its earliest moments lay beyond the reach of current tools. Still, scientists pressed forward. Cosmological models were proposed that sought to tame the singularity. Some imagined a universe that oscillated in endless cycles, collapsing and expanding without ever truly beginning. Others suggested hidden variables or new forms of matter that might soften the sharp edge of the singularity, stretching the point of infinite density into something more manageable. But these ideas were fragile, resting on speculation more than evidence, and the mystery only deepened. The instruments of the time, though revolutionary in their era, were still crude compared to the cosmic scale of the questions being asked. Astronomers strained through telescopes, hoping to glimpse galaxies at ever greater distances, and thus peer further back into history. Yet the earliest light of the cosmos remained hidden, veiled behind a curtain of opacity from the universe's first few 100,000 years. For all their ingenuity, the scientists of the early 20th century could not pierce that barrier. Meanwhile, theoretical physicists began to realize that the universe might carry within it an afterglow, a faint radiation left over from its fiery birth. This idea, first suggested in the 1940s, hinted that if the cosmos had truly begun in an unimaginably hot and dense state, then the remnants of that heat might still bathe the universe, cooled and stretched by expansion into a faint, invisible whisper. If such radiation existed, it would be a relic of the beginning itself, an echo frozen across the heavens. Yet in those early decades, it remained only a hypothesis, awaiting discovery. Through these early investigations, the paradox at the heart of cosmology refused to be silenced. Every attempt to describe the singularity seemed to push physics to its breaking point. The expansion traced backward demanded an origin, but the language of science faltered at time zero. The earliest explorers stood at the threshold of a profound mystery, sensing that the answers lay just beyond the reach of observation, waiting for a future generation of instruments and ideas. The seeds of deeper discovery had been planted, but the soil of knowledge was not yet ready to bear fruit. As the 20th century unfolded, the discovery of cosmic expansion demanded a deeper reckoning. If the universe was moving outward, carried on the invisible tide of space-time, then its past carried with it a haunting implication. Rewound far enough, the galaxies and stars, the atoms and particles, all would converge toward a singular origin. To the physicists of the age, this singularity was not simply a mathematical point. It was a place where their most trusted equations broke apart, scattering like shards of glass. Einstein's relativity could describe the bending of light around stars, the dance of planets, even the warping of space itself. But when turned upon the origin of everything, it yielded infinity's densities without limit, curvatures beyond comprehension. It was a sign that the tools of science were brushing against the very edge of their validity. These infinities were not just technical inconveniences. They were warnings, glaring red lights at the frontier of knowledge. For to describe the beginning as a singularity was to admit that the laws of physics dissolved at the moment they were most needed. Some attempted to look past the paradox, proposing cosmological models that could soften or even erase the singular point. Perhaps the universe did not begin in a singular moment of creation, but oscillated in cycles, collapsing and rebounding in an endless rhythm of death and renewal. Others imagined strange forms of matter or hidden symmetries that might smear the singularity into something finite. These were bold visions, but in the absence of evidence, they remained fragile scaffolds of speculation. The instruments of the time were too limited to pierce the veil of the earliest universe. Telescopes strained against the boundaries of visibility, gathering the faint light of distant galaxies, yet the deeper past remained inaccessible. For, in the beginning, the cosmos was not transparent. It was a seething plasma, particles and photons locked together in a fog too dense for light to travel. Only when the universe cooled, hundreds of thousands of years after its birth, did that fog lift, allowing the first light to move freely across the void. This meant that no matter how far astronomers looked, they would always encounter a horizon, wall of cosmic opacity beyond which their instruments could not see. And yet, in the stillness of theory, some physicists began to imagine another kind of evidence. If the universe had truly been born in fire, then surely that fire must have left behind an afterglow, a radiation stretched thin by expansion, cooled by billions of years, but still present, suffusing every corner of space. In the 1940s, George Gamow, Ralph Alpha, and Robert Herman proposed that such a relic should exist, cosmic whisper from the moment of creation itself. They predicted it would be faint, almost imperceptible, a glow in the microwave region of the spectrum. Few listened. The idea was intriguing, but no instrument of the time could hope to detect such a signal. As models multiplied and speculations grew, attention settled over the field. For some, the very act of peering toward origins felt perilous, too close to philosophical terrain long considered outside the reach of science. If the universe had a beginning, then what was before that beginning? If time itself started at the Big Bang, could there even be such a thing as before? The paradox hung like a shadow, a silent reminder that cosmology was not only a science of stars and galaxies, but also a meditation on existence itself. The early investigations revealed the scale of the challenge. Relativity could guide the way, but stumbled at the singularity. Telescopes could gather the faint light of distant worlds, but not the first light of creation. Theories could gesture toward an afterglow, but no proof could yet be found. The mystery of the beginning held its silence. It was as if the universe had chosen to conceal its earliest secret behind a veil, daring humanity to look deeper, to invent new tools, to imagine beyond the boundaries of thought. For decades, the idea of an afterglow from creation lingered like a faint rumor, whispered in papers that few read and fewer believed. The prediction by Gamow, Alpha, and Herman of a relic radiation, cooled across eons, drifted in obscurity, waiting for instruments sensitive enough to hear it. Then, in 1965, the universe itself broke its silence. Two young radio engineers at Bell Labs, Arno Penzias and Robert Wilson, set out to calibrate a new microwave antenna designed for satellite communication. What they found was not silence, but a persistent noise, a background hiss that refused to disappear. They checked their instruments, recalibrated, even cleaned out the nests of pigeons that had settled in the antenna, suspecting droppings as the culprit, but nothing removed. The signal, the noise came not from the Earth, not from the atmosphere, not even from the Milky Way. It came from everywhere, from every direction, with the same intensity. They had stumbled upon the fossil light of the universe, the cosmic microwave background. The afterglow of the Big Bang stretched across all of space. In that moment, speculation became evidence. What had been a theoretical curiosity hardened into observation, as unmistakable as the light of a star. The discovery was a revelation. It was not only proof that the universe had once been hot and dense, but that it carried the memory of that moment across the vastness of time. Every inch of sky glowed with the same faint radiation, the residue of an origin. The steady-state universe, once defended with conviction, could not withstand this proof. An eternal cosmos, replenished with newly created matter, had no place for such an afterglow. The cosmic microwave background declared, without ambiguity, that the universe had been born in fire. In the years that followed, humanity began to map this ancient light with increasing precision. The COBE satellite, launched in 1989, confirmed the spectrum of the radiation with astonishing accuracy, showing that it was a perfect black body curve, exactly what theory had predicted for the cooled remnant of a primordial fireball. Later, WMAP and the Planck mission painted the universe with even finer detail, revealing minute fluctuations in the background, tiny ripples in temperature that recorded the first seeds of structure. Those slight variations, mere fractions of a degree, were the fingerprints of the earliest quantum fluctuations, magnified by cosmic inflation, destined to grow into galaxies, stars, and eventually life. The cosmic microwave background was not only proof of a beginning, it was a map of creation itself. And yet, with every layer of precision, the paradox deepened. The universe now had a measured aged 13.8 billion years, the moment of transparency, when the first light broke free, could be charted to a mere 380,000 years after the Big Bang. But beyond that horizon, the radiation could not speak. The singularity still lay hidden beyond the veil of the Planck epoch, where physics faltered. The cosmic microwave background was both revelation and boundary. It answered the question of whether the universe had a beginning, but it sharpened the deeper riddle: what existed before time began? To gaze upon this ancient light was to stare into a mirror of origins, a reflection carried for billions of years across the dark. It was proof that the cosmos was not eternal, but finite in age, finite in history. And yet, even as the evidence silenced the old debates, it opened a silence, more profounder silence of thought itself. For the discovery of the afterglow told humanity how the universe began, but not why, and not what lay on the far side of that impossible boundary. The radiation whispered of a beginning, but its voice stopped at the threshold of time. Beyond that, the universe still refused to answer. For centuries, the question of cosmic origins had been a theater of speculation, a debate carried by equations, philosophy, and imagination. But in the middle of the 20th century, the universe itself revealed its testimony, not in words, not in symbols, but in a faint whisper of light. It was 1965 when two radio engineers, Arno Penzias and Robert Wilson, were tasked with refining a new communication antenna at Bell Labs. Their concern was practical, not cosmic. Yet, as they calibrated the massive, horn-shaped instrument, a persistent hiss filled their receivers, a static that clung no matter where they pointed the antenna. They accounted for earthly interference, eliminated instrumental noise, even went so far as to clean away the pigeons and the traces they left inside the dish. Still, the hiss remained, stubborn and omnipresent, uniform across every direction of the sky. Unbeknownst to them, what they were hearing was not noise at all. It was the universe speaking in the language of relic radiation, the faint afterglow of its own birth. This was the cosmic microwave background, the fossil light of creation itself, stretched and cooled by billions of years of expansion. Just as a campfire leaves a lingering warmth long after its flames have gone, the universe carried with it the signature of a fireball so immense it defied comprehension. what Gamow, Alpha, and Hermann had predicted in theory nearly 2 decades earlier. Penzias and Wilson had stumbled upon by chance. Their static was not interference, it was evidence. It was the confirmation that the universe had once been far hotter, denser, and younger than anyone could imagine. For this revelation, the 2 men would be awarded the Nobel Prize, though they themselves had not set out to prove or disprove cosmological theories. They had simply listened carefully, and the cosmos had whispered its secret. With that discovery, the great debate of the 20th century shifted irreversibly. The steady-state theory, which had clung to the hope of an eternal, unchanging universe, collapsed under the weight of this evidence. A cosmos that bore the memory of an origin, encoded in its very fabric, could no longer be portrayed as timeless. The Big Bang, once dismissed by many as a speculative story, stood now as reality, written across every inch of the night sky. No longer was expansion merely an observation of galaxies receding. Now there was proof of a beginning, proof of fire, proof of time's birth. As technology advanced, humanity turned its instruments directly upon this afterglow. In 1989, the COBE satellite lifted into orbit, its mission to measure the cosmic microwave background with a precision impossible from Earth. The data it returned was nothing short of extraordinary. The radiation followed a perfect black body curve, confirming beyond doubt that it was indeed the cooled remnant of a once radiant cosmos. Even more astonishing were the faint ripples COBE detected, minute variations in temperature. Only 1 part in 100,000. These fluctuations, invisible to the naked eye, were the seeds of structure, the delicate imprints of quantum irregularities stretched across the infant universe. From these tiny ripples, gravity would one day sculpt galaxies, stars, and eventually worlds. In those faint, uneven whispers, the blueprint of cosmic architecture was revealed. A decade later, the Wilkinson Microwave Anisotropy Probe, WMAP, sharpened the picture. Its measurements traced the ripples across the heavens with unprecedented clarity, mapping the infant universe as it had appeared 380,000 years after its birth. Through this cartography of the first light, the age of the universe was pinned with astonishing precision: 13.8 billion years. In those numbers, a timeline of everything was etched, from the ignition of stars to the formation of life. No longer was the universe an immeasurable expanse without anchor. It was a story with a beginning, a history with a clock. Then, in 2009, the Planck satellite refined the vision still further, its sensitive detectors peeling back the cosmos in exquisite detail. What emerged was the most accurate portrait of the early universe ever achieved. A tapestry of light and shadow, where temperature differences of mere millionths of a degree spoke of the deepest laws of physics. Planck revealed the symmetry and imperfections that shaped the destiny of all things, showing how the quantum fluctuations of the earliest instants had become the galaxies of today. To look upon the Planck map was to gaze into the first visible memory of the universe, a portrait painted not with brushstrokes but with photons that had journeyed for nearly 14 billion years. And yet, every new layer of clarity brought with it a sharper paradox. For if the cosmos had a measurable age, if its story could be traced back to a fiery origin, then the question became impossible to avoid: what lay before? The cosmic microwave background was the oldest light the universe would ever allow humanity to see, but it was also a wall, a horizon beyond which no radiation could pass. The singularity, the first instant, remained veiled in silence. The afterglow told of a beginning, but it also set the boundary of human knowledge, drawing a line. At the Planck epoch, where time itself seemed to dissolve. Thus, the triumph of observation was also a deepening of mystery. With COBE, WMAP, and Planck, humanity had captured the echoes of creation and confirmed beyond doubt that the universe had a beginning. But those same echoes raised the most unsettling question of all. If time began with the Big Bang, what does it mean to speak of before? If the cosmos is the totality of existence, what does it mean to ask what it expands into? The static of Penzias and Wilson had opened a door not just into the history of the universe, but into the edge of thought itself. The proof of a beginning was not the end of the story. It was the beginning of a deeper silence and abyss where physics trembles and imagination strains toward answers that may forever remain beyond the grasp of science. The confirmation of a cosmic beginning did not settle the question of origins. It sharpened it into something far more profound. If the universe emerged in a single incandescent moment, what lies at the threshold where time itself seems to ignite? The Big Bang, for all its triumph in describing expansion, did not explain its own spark. Instead, it left science staring into a singularity, a point where equations fracture and infinities flood the page, where every attempt at calculation dissolves into paradox. General relativity, Einstein's grand description of gravity and space-time, can trace the universe backward with exquisite precision, but only so far. As the equations press toward the moment of birth, densities soar beyond measure. Temperatures climb beyond definition, and space-time itself collapses into a boundary that mathematics cannot cross. In that place, infinities do not describe reality, they mark its breakdown. A singularity is less a physical thing than a signpost of ignorance. A mathematical flare declaring, the laws known so far cannot reach beyond this veil. Here, the quantum world enters, whispering of possibilities where relativity fails. Quantum mechanics, with its restless uncertainty, does not yield easily to the smooth curvature of Einstein's spacetime. Instead, it suggests a granularity, a restless foam at the smallest scales where space and time flicker in and out of existence. The Planck epoch, an unimaginably brief instant, 10 to the minus 43 seconds after the beginning, marks the frontier where both theories must unite, but where no unifying theory yet exists. It is here that physics trembles most profoundly. For, in that abyssal sliver of time, the seeds of all that followed were set. Yet human knowledge falters at the edge of its reach. To bridge this abyss, cosmologists have turned to the language of inflation, proposed by Alan Guth in the early 1980s. Inflation describes a breathtakingly brief moment when the universe expanded faster than light itself, not in defiance of relativity, but through the stretching of space. In less than a heartbeat, quantum fluctuations were stretched to cosmic scales, becoming the patterns later etched into the microwave background. Inflation explains the smoothness of the cosmos, the near uniformity of its earliest light, while also accounting for the tiny ripples that seeded galaxies. Yet inflation itself demands a prelude, an energy field poised in an unstable state, a false vacuum waiting to tumble. Even as it solves mysteries, it opens new ones. What ignited inflation and what ended it? Philosophical weight presses against these equations. If inflation was real, does it imply that our universe is but one bubble in a frothing multiverse, each bubble a cosmos with its own laws and destinies? If so, then the question of a beginning becomes blurred, for beginnings may be countless, scattered across an eternal sea of creation. Yet such ideas remain speculative, their evidence indirect at best, shimmering at the edge of mathematics, but not yet carved into data. Meanwhile, telescopes and satellites strain to look closer, though light itself cannot carry them past the wall of the microwave background. The Planck epoch remains hidden, a realm where observation falters, where physics whispers but does not yet speak. To peer further, scientists must turn not to light, but to gravity ripples in space-time itself. Primordial gravitational waves that may have been imprinted in the earliest instants. Should they ever be detected, they would be the faint tremors of creation, carrying information from a time when the universe was younger than any light can reveal. And so, the paradox deepens. The closer science approaches the origin, the more the universe conceals. Proof of a beginning has become proof of mystery, sharpening the ancient questions into forms that haunt both physics and philosophy. If time itself was born in the Big Bang, the word before dissolves into paradox. For how can there be a before when there is no time? If space was created in that instant, the question into what does it expand becomes equally fragile. For expansion requires no external void, is the growth of space-time itself, needing no vessel beyond its own existence. The cosmic microwave background proved that the universe had a birth, but in doing so, it pulled the curtain back only, to reveal a deeper abyss. Beyond the threshold of light, beyond the reach of current equations, lies a silence more profound than the hiss that Penzias and Wilson once heard. It is the silence of origins themselves, where knowledge falters and imagination strains toward an unknown horizon. Here, science and philosophy converge, standing together at the edge of a cosmic ocean, staring into a darkness that no instrument has yet pierced, and wondering not only how the universe began, but why it exists at all. The more clearly the universe revealed its birth, the more mysterious that birth became. The Big Bang was no longer speculation. It had been etched into the very sky in the faint glow of ancient light. Yet behind that light lay a silence science could not break. General relativity, so elegant in describing the vast curves of space and time, faltered when driven back to the first instant. It led to a singularity, an infinitesimal point of infinite density and temperature where its mathematics unraveled, yielding infinities that mocked comprehension. A singularity was not a description of reality, but a confession of ignorance, a signpost declaring the breakdown of the very laws that had carried humanity so far. The singularity problem sharpened the paradox of origins. If the universe truly began in such a point, then physics itself collapses at the threshold of creation. But if physics collapses, how can one speak of a beginning at all? It is here that quantum mechanics entered the frame, bringing with it a different language, one shaped not by certainties but by probabilities, not by smooth curves but by restless fluctuations, where relativity envisioned the universe as a seamless fabric. Quantum mechanics revealed a flickering sea of uncertainty, a world where nothing is ever perfectly still and even emptiness seethes with potential. At the intersection of these two visions lies the Planck epoch, the very first sliver of time after the Big Bang. It lasted less than 10 seconds, a duration so brief it eludes all ordinary comprehension. In that instant, gravity itself may have been united with the other fundamental forces before splintering into the forms seen today. Space and time, as familiar constructs, may not even have existed in any recognizable sense. Instead, they may have emerged from a quantum foam, a storm of fleeting geometries bubbling in and out of being. No experiment has yet pierced this veil, and no telescope can look back so far. The Planck epoch remains hidden behind the wall of theory, its truths beyond the reach of present science. Speculative visions rise to fill the void. Some imagine a bouncing universe, collapsing and rebounding eternally. Each Big Bang not the first, but merely one in an endless cycle. Others speak of emergent time, where the flow of moments is not fundamental, but arises from deeper laws, just as temperature arises from the dance of unseen particles. In such views, the very notion of a before may dissolve. If time itself was born with the cosmos, then asking what came before is like asking what lies north of the North Polar question, whose very frame collapses upon itself. The paradox grows sharper the closer one looks. To say the universe began is to acknowledge a boundary, but boundaries demand a context, and here the context may not exist. It is a riddle that blurs the line between physics and philosophy, between mathematics and metaphysics. The singularity problem is not merely a technical flaw in equations. It is the sign of a deeper truth still hidden, waiting to be discovered. In its silence, it whispers of realities not yet imagined, of laws not yet written, of mysteries that stretch beyond the horizon of thought itself. And so the mystery deepens. The universe, which once seemed explained by the triumph of the Big Bang, now seems even more elusive. Every answer reveals a greater question. Every discovery sharpens the edge of wonder. Humanity stands before the abyss of origins, staring into the darkness where time itself may have been born, and asks with trembling voice if there was a beginning. What breathed the spark of existence into being, and, if there was not, what timeless reality sustains the cosmos from beyond all? Beginnings. Some of the earliest attempts to make sense of this abyss came from the boldest voices in 20th century physics. If relativity collapsed into singularities and infinities, perhaps a deeper theory was waning beneath. String theory offered one such vision. Instead of treating the universe as built from indivisible points, it proposed that the most fundamental building blocks were vibrating filaments of energy, loops and strings resonating at frequencies that determined the nature of particles themselves. In this framework, gravity was not an alien force grafted onto quantum mechanics, but a natural vibration of the strings themselves. Yet string theory carried a strange consequence: to remain mathematically consistent, it required more dimensions than the three of space and one of time experienced in daily life. These hidden dimensions might be curled so tightly they escape perception, or perhaps they stretch into realms forever inaccessible. If true, the beginning of the universe might not be the birth of everything, but only the blossoming of our particular four-dimensional shadow within a grander, higher-dimensional stage. Another contender emerged in the form of loop quantum gravity, where string theory dissolved the point into a vibrating thread. Loop quantum gravity dissolved space itself into discrete chunks, woven together like an invisible fabric of loops and nodes. In this view, geometry comes in quanta, indivisible units of volume and area, meaning space cannot be compressed infinitely. At the supposed singularity, space does not collapse to nothing but rebounds, producing a new expanding universe. The Big Bang becomes a big bounce, one act in an infinite cosmic cycle, where each universe rises from the ashes of a previous collapse. Such theories are still tentative, fragile bridges stretched across a gulf of ignorance, but they carry with them the promise of dissolving the paradox of beginnings into a deeper continuity. And yet, even as mathematics dared to peer behind the veil, a philosophical unease lingered. What does it mean to speak of time before time? If the cosmos truly emerged from quantum foam, does that mean the universe arose from nothing or from a restless sea of potential that has no origin? The language bends under the weight of the question. For physicists, nothing is never truly nothing. It is not an empty void, but a roiling field of energy, where particles flicker in and out of being, their brief existence allowed by the uncertainty that governs all things. If this quantum vacuum existed before the Big Bang, then perhaps the universe emerged as a fluctuation, a blossom from the fertile soil of the void. But then one must ask, where did this vacuum itself come from? Is it eternal? Or is it itself a product of laws written in a realm beyond the grasp of observation? The closer one approaches this horizon, the more language frays. Words such as before and after lose their coherence when time itself is no longer fundamental. To imagine the birth of time is to confront the limits of imagination itself. In such realms, even the most disciplined scientific thought begins to touch the edges of philosophy and metaphysics. Some physicists have dared to suggest that time is emergent, like temperature or pressure properties that arise only when the underlying constituents are considered together. If so, the very flow of moments, the heartbeat of existence, is not the foundation of reality but a surface effect of something deeper. Beneath time, beneath causality, lies a realm without sequence, without then or now. And if that is true, then the question of what came before evaporates. For before has no meaning where time does not flow still. The human mind, bound by experience, struggles to accept such abstractions. To say the universe has no beginning is as unsettling as to say it emerged from a singular spark. Both evoke a boundary, a wall where reason falters, and so humanity oscillates between visions. A cosmos that cycles eternally, a cosmos that bubbles from a deeper field of potential, or a cosmos that is finite yet Each possibility carries its own weight of wonder, its own challenge to understanding. Each sharpens the paradox at the center of all inquiry, as satellites like COBE, WMAP, and Planck mapped the infant light of the cosmos with exquisite precision. They traced not only the contours of the early universe, but also the boundaries of ignorance. The cosmic microwave background revealed fluctuations, tiny differences in temperature that later grew into galaxies and stars. Yet it also carried silence, a wall beyond which no observation could pass. The Planck epoch, the unimaginably brief first instant, remained hidden. No data reached beyond it. No telescope could pierce it. The first moment was shrouded in eternal darkness, as though the universe itself had sealed away its origin. And here the mystery becomes not merely scientific, but existential. To ask what happened at time zero is to confront not just equations, but the human longing for beginnings. Every culture has told stories of creation. Every civilization has imagined a moment of emergence. Science, in its precision, replaced myth with measurement, but even here the same questions linger. What does it mean for existence to begin? What does it mean for reality to be born? And what, if anything, lies beyond that birth, in the deep silence of the cosmic background? One hears not only the echo of the Big Bang, but also the echo of questions older than civilization itself. The singularity problem is not just the failure of relativity. It is the mirror in which humanity sees the limit of its knowledge, and yet, within that limit lies possibility. The failure of one theory is the seed of another. The collapse of Certainty is the soil of deeper truth. The universe remains veiled, but in the very act of veiling, it invites discovery. At the furthest frontier of modern thought, the universe reveals itself not as a solved riddle, but as a shifting horizon, always receding as understanding advances. Every telescope, every equation, every bold attempt to peer into the origin of time itself eventually arrives at a boundary, a silence that refuses to yield. It is here, at the edge of certainty, where science takes on its most daring and fragile forms. The questions grow sharper. What lies beyond the Big Bang? Was it the first of all beginnings, or merely one chapter in an infinite sequence of cosmic births and deaths? The answers offered are not definitive truths, but visions, mathematical landscapes drawn from the deepest currents of theoretical physics. They are bridges stretched across a gulf of ignorance, fragile yet luminous, reaching into a realm where observation cannot yet follow. One of the most ambitious of these visions is string theory. In this bold reimagining, the universe is not composed of point-like particles, but of vibrating strings, loops of energy whose resonances create the spectrum of matter itself. Every electron, every quark, every photon is not a separate entity, but a different song sung by the same universal instrument. In such a framework, gravity emerges not as a stubborn anomaly, but as a natural note within the grand symphony. Yet this elegance carries with it a staggering implication. The universe requires more dimensions than those seen by the human eye. Hidden folds of space, perhaps 10 or 11 dimensions in total, may be compacted, curled so tightly they evade perception. Within these unseen realms could reside the structures that existed before the Big Bang, pre-geometric states of energy where time and space had not yet unfurled. To consider this possibility is to imagine the Big Bang not as the birth of everything, but as the unfolding of a higher dimensional seed into the four-dimensional stage humanity inhabits, where string theory stretches space into hidden corridors. Loop quantum gravity breaks it into discrete atoms of geometry. Space is no longer continuous, but woven from indivisible loops, a network of quanta that builds the fabric of reality. In this picture, time and space cannot be crushed into singularity, for they resist infinite compression. Instead, when a universe contracts to its smallest possible state, it rebounds. The Big Bang becomes a bounce, one in a series of cosmic cycles, where universes rise and fall endlessly like breaths upon an eternal ocean. The concept is daring, almost mythic in its resonance, yet born not of ancient legend, but of mathematics, of the attempt to reconcile relativity with quantum law. If true, then what is observed as a beginning is only a turning point, a moment in a cycle far older than any single universe. But even before such cycles might unfold, another force entered. The cosmic story and expansion so violent and brief it defies human intuition. This was inflation, a fraction of a second when the universe grew faster than light itself, stretching quantum fluctuations into the seeds of galaxies. Inflation explains the smoothness of the cosmos, the uniform glow of the microwave background, and the delicate distribution of matter across the stars. Yet the mystery deepens. What preceded inflation? Was it triggered by a field of energy, or was it an inevitable phase in a larger cycle of expansion and collapse? Some physicists suggest that inflation never truly ends. If so, while one bubble universe stabilizes into galaxies and stars, other bubbles continue to inflate and fragment, spawning new universes endlessly in a vast, ever-growing multiverse. In this view, the Big Bang was not unique, but one firework. In an infinite cosmic display, black holes to whisper of hidden universes. In the depths of their collapse, where gravity overwhelms all resistance, a singularity forms a point where space and time seemingly break. But what if that singularity is not the end, but a beginning? Some theories suggest that the interior of a black hole may birth new universes, with their own space, their own time, and perhaps even their own laws of physics. In such a vision, our universe could itself have been born from the death of another, the collapse of a massive star in some parent cosmos giving rise to the fireball of our beginning. The multiverse, in this telling, is not only a froth of inflationary bubbles, but a branching tree of black hole progeny, where each collapse becomes a creation. As these models multiply string landscapes, quantum bounces, eternal inflations, black hole births, they reveal not certainty, but humility. Each theory is bold, each rests on mathematics and reason, yet all remain untested against the silence of the first moment. The data available: microwave backgrounds, particle collisions, gravitational waves reach far, but not far enough. No observation has yet pierced the veil of the Planck epoch. No instrument has carried human eyes into the first 10 seconds. In that absence, speculation blooms, but always tethered to the discipline of science. The true measure of progress lies not in claiming absolute answers, but in refining the questions, in building frameworks that future generations may one day test. And so, at the extreme edge of science, there is both audacity and restraint. Audacity to imagine universes beyond universes, dimensions beyond sight, cycles beyond time. Restraint to admit that these remain hypotheses, possibilities suspended between mathematics and mystery. The paradox of beginnings sharpens here. Perhaps there was no beginning at all, only transitions from one state to another. Perhaps beginnings are illusions born of limited perspective, or perhaps there truly was a singular genesis, a first moment, when existence ignited from nothing into everything. At this frontier, science does not silence wonder, it deepens it. Each new theory illuminates not an answer, but a pathway into the unknown. The closer one approaches the question of before time, the more it becomes clear that the question itself may dissolve, replaced by a recognition that time, causality, and even existence are not as fixed as they seem. What lies beyond the Big Bang may forever remain veiled, yet in striving to reach it, humanity glimpses something greater, the vastness of possibility, the unending ocean of mystery from which all discovery is drawn. In some corners of theoretical physics, the story takes an even more radical turn. Roger Penrose, Nobel laureate and architect of deep insights into black holes and space-time, has suggested that the universe may be far older than the Big Bang itself. His idea, known as conformal cyclic cosmology, imagines that what is called the end of the universe and what is called its beginning are not opposites but linked. As the universe expands toward emptiness, with black holes evaporating and matter dispersing into a thin bath of radiation, its scale loses all meaning. Time, stripped of mass and structure, becomes indistinguishable from the timelessness that marked the beginning. In this strange symmetry, one eon flows seamlessly into another, the death of one cosmos becoming the birth of the next. If true, then the faint background of the universe may carry whispers of events from cycles long past, fossil imprints of a cosmos that lived and died before this one began. Other visions turn not toward cycles, but toward quantum genesis itself. In some interpretations of quantum cosmology, the universe might have emerged spontaneously, without cause. In the same way particles flicker into existence within the vacuum of space, the Heisenberg uncertainty principle, which allows energy to arise briefly from nothing, may scale upward to the cosmos itself. In such scenarios, the universe requires no external trigger, no hand to set it in motion. Its existence is permitted. By the rules of probability, a quantum fluctuation magnified into a reality that did not collapse back into nothingness. This is not to say that the universe is trivial or accidental, but rather that its possibility was embedded in the very structure of physical law itself, even before there was space or time to contain it. Quantum cosmogenesis carries profound philosophical weight. If universes can arise from fluctuations, then perhaps they do so endlessly, not only once, but as a natural feature of reality. Some theorists link this to the inflationary multiverse, where each new universe buds off into its own domain, isolated and self-contained. In this boundless branching, physics becomes not a single narrative, but a vast library, with universes as its volumes, each with its own constants, its own laws, its own possible histories. Most may be barren, devoid of complexity, collapsing, swiftly or stretching in sterile stillness. But in a few, the delicate balance of forces gives rise to stars, to planets, to the strange phenomenon of consciousness reflecting on its own existence. Our universe, then, may not be inevitable, but one among countless variations. Its life-giving conditions, a rare but not unique arrangement within an infinite cosmic sea. Yet even these grand constructions cannot claim finality. They are maps drawn at the border of the unknown, sketches of terrains glimpsed but not traversed. The limits of observation impose humility. No experiment has yet confirmed the existence of extra dimensions, nor proved that space-time is granular. At its core, the evidence for inflation is powerful, yet its details remain uncertain, and the multiverse, by definition, may forever elude direct detection. Still, these theories matter deeply, for they sharpen the frontier, clarifying where knowledge ends and imagination begins. They frame the questions that guide future generations. The experiments not yet conceived, the instruments not yet built. The extreme edge of science is not a wall, but a horizon. It invites forward motion, knowing full well that the horizon will retreat. To contemplate what may lie beyond the Big Bang is to look not only into the depths of the cosmos, but into the nature of human inquiry itself. The more daring the theories become, the more they remind us that certainty is rare, and that truth, if it exists in full, may always lie just out of reach. Yet in that distance there is wonder. There is the recognition that existence is larger than comprehension, that the universe, whether singular, cyclical, or infinite, will always remain partly veiled. And in that veil lies the poetry of science, not the possession of answers, but the pursuit of them, a pursuit that carries thought into realms as strange and boundless as the cosmos. It seeks to understand. The story of the universe's beginning cannot be told without entering the arena of its leading theories, those fragile yet formidable frameworks that attempt to reach into the silence before the first light. Among them, inflationary cosmology stands as the most widely accepted. In this vision, the infant universe, born in less than a trillionth of a second, did not simply expand. It erupted, ballooning at speeds beyond imagination, stretching space-time itself like a canvas pulled taut. The theory of inflation explains why the cosmos today appears smooth on the largest scales, why distant regions seem to share the same temperature despite being too far apart to exchange information by the speed of light. It accounts for the seeds of galaxies, tiny quantum fluctuations, frozen and magnified into the architecture of stars and clusters. Inflation offers clarity, but also mystery, for while it explains the shape of the universe, it raises the haunting question of what mechanism could ignite such a colossal burst, and whether it is part of a larger, eternal process of universe making into. This uncertainty enters the strange world of quantum cosmology. Here, the universe itself is described as a wave function, a mathematical object representing all possible histories simultaneously. Instead of a singular beginning, there are many beginnings layered in probability, awaiting the unfolding of reality. This framework does not imagine time as linear, but as something more elusive, dimension that itself emerges from quantum rules at the foundation of existence. The concept of a single timeline gives way to a haze of potential, where what we call the universe is but one path taken from an infinite array. It suggests that before the first second, the cosmos was not nothingness, but possibility itself, suspended in a state beyond ordinary comprehension. The Hartle-Hawking proposal sharpens this vision. In this model, the universe has no edge, no sharp line where time begins. Instead, time may behave like space itself, curving smoothly at its origin. Just as the Earth has no edge at its poles but bends into continuity, the cosmos may have no singular boundary, but transition softly from a timeless quantum realm into the temporal expanse we inhabit. In this picture, asking what came before the Big Bang may be like asking what lies north of the North Pole. The question dissolves into the geometry itself, and the paradox fades into a kind of mathematical elegance. Still, not all theories paint the beginning as the final word. Cyclic models imagine a universe without a true birth, one that breathes in vast rhythms of expansion and contraction. Instead of an absolute beginning, there is a series of bounces, each cosmic collapse followed by a rebirth. In this way, the Big Bang becomes not a singular origin, but a transition. One beat in an eternal pulse of universes arising, fading, and rising again. Such models remain speculative, yet they capture something deeply resonant, the intuition that perhaps the universe, like life itself, is woven into patterns that transcend death and beginning, carrying forward into new forms. Despite these diverse visions, a quiet consensus threads through the heart of modern physics. The laws we know can describe the universe exquisitely from the first fractions of a second onward, but not the moment before. The Planck epoch, the singularity, the imagined boundary, these remain shrouded. At that edge, general relativity and quantum mechanics still speak in conflicting tongues, their languages refusing to merge, and so science lingers at the threshold, able to map the afterglow but not the spark, to chart the unfolding but not the moment of ignition. The mainstream theories stand as remarkable achievements, weaving the mathematics of inflation, quantum, probability, and geometry into a tapestry that extends nearly to the beginning. Yet they also remind us of the humility embedded in the scientific endeavor. For no matter how refined the models, no matter how precise the data, the question of before may lie forever in the realm where language falters and imagination takes hold. And in that lingering silence, the mystery only deepens, inviting wonder as much as understanding, leaving the edge of creation not as an answer, but as a horizon that beckons still. Inflationary cosmology, though elegant in its ability to smooth the wrinkles of the early universe, is not a simple story of expansion. It is a tale of hidden energy fields, of an entity called the inflaton, a hypothetical force that may have driven the universe into its sudden, exponential growth. For a fleeting moment, the universe doubled in size, again and again, in less than a heartbeat, expanding from subatomic scales to dimensions vast enough to contain everything we now observe. Yet the mechanism of this inflation remains unknown. Was it a fundamental field written into the laws of physics, or the echo of deeper processes hidden beyond our perception? The observable fingerprints of inflation, the faint patterns etched into the cosmic microwave background, the delicate ripples of temperature that became the scaffolding for galaxies, that something extraordinary took place in that first fraction of a second. But behind that veil lies silence. Inflation explains the how, but not the why, leaving cosmologists staring into the abyss of its origin. Quantum cosmology dares to cross that abyss. By treating the universe as a wave function, it reframes the question of beginnings. In quantum mechanics, particles are not points but probabilities, smeared across possibilities until observation pins them into reality. Applied to the entire cosmos, this means the universe itself once existed in a superpositioner cloud of possible histories, each equally real until, somehow, one crystallized into the fabric of space-time. In this vision, there is no single path, no singular line of cause and effect. Instead, the universe is born from probability, unfolding not from a prior moment, but from a sea of potential states. This is a profound shift, for it suggests that what we call the beginning is not the appearance of something from nothing, but the emergence of actuality from possibility. The Hartle-Hawking proposal takes this further, transforming the very geometry of time. Imagine tracing the Earth's surface toward its North Pole. At first, latitude circles shrank, becoming smaller and smaller, until at last they vanish into a single point. Yet the pole itself is not a boundary, it is simply a smooth turning of geometry. In the same way, the universe may not have a sharp beginning, but a rounded transition, where the concept of time itself dissolves into a timeless state. At this deepest level, the question what came before loses meaning, not because there is no answer, but because the question is misplaced. Time may not be a river that flows eternally, but a quality that emerges only after the cosmos finds its shape. What we call the Big Bang might then be less a birth and more a transformation, a passage from the timeless into the temporal, cyclic models. By contrast, refuse the notion of a unique beginning. They see the universe not as a solitary act, but as a performance repeated across cosmic ages. In these models, the cosmos expands and contracts in endless rhythm, each collapse giving rise to a new expansion, each Big Bang following a big crunch. The idea resonates with ancient intuitions, with myths that imagined creation as eternal recurrence. Modern physics reframes it with equations of energy, entropy, and geometry. One version, the ekpyrotic model, proposes that our universe's birth was the collision of higher dimensional brains, vast sheets of reality colliding in a greater dimensional space. Another envisions a cosmic bounce, where quantum gravity prevents the total collapse of space-time, rebounding instead into new growth. If true, then our universe is not the first, nor will it be the last. It is but one verse in an infinite symphony of beginnings and endings. Yet even these bold theories carry a note of humility. Inflation explains much, but cannot reach the spark that ignited it. Quantum cosmology reframes beginnings, but depends on equations that remain untested. The Hartle-Hawking proposal dissolves the edge of time, but exists only in the language of mathematics. Cyclic models capture imagination, but remain speculative, lacking the decisive evidence that could lift them into consensus. The scientific frontier, despite its dazzling reach, still falters at the threshold. What happened at the Planck scale 10 seconds after the supposed beginning remains hidden. General relativity curves into infinities. Quantum mechanics refuses to stay silent. Their union, long sought, still lies out of reach, and so the mainstream theories converge on a shared boundary. Physics can trace the unfolding of the cosmos from nearly its first heartbeat, but not the silence before. Beyond that boundary, questions deepen into mystery. Was there truly a beginning, or only transitions? Is time a fundamental thread, or an emergent pattern woven from deeper laws? Could the fabric of space-time itself arise from something more primal, something beyond geometry, beyond causality? In the silence where equations break, imagination enters, but always with the recognition that the edge of knowledge remains. For now, unbroken, eternal inflation stretches the imagination into realms far beyond what observation alone can confirm. In this framework, the inflationary burst that sculpted the early universe is not a singular, fleeting event, but a process without end. While regions like our own may settle into expansion that eventually slows, other regions remain trapped. In the inflating phase, birthing new domains again and again. Each of these domains becomes its own universe, a bubble expanding within an infinite cosmic sea. Some may resemble ours, with galaxies, stars, and laws of physics familiar to us. Others may be profoundly alien, governed by different constants, different particles, even different numbers of dimensions. If this vision is true, then the universe we know is but a single drop in an endless storm of creation, a fragile bubble adrift among countless others, forever beyond our reach. The model offers another radical reimagining of beginnings. Instead of a singular birth, it envisions the universe as the aftermath of a collision between vast higher-dimensional brain cements, sheets of reality suspended in a greater spatial arena. According to this picture, our cosmos may not be all that exists, but one of many membranes floating in a higher-dimensional bulk. When these branes collide, the impact generates the energy of a Big Bang, igniting a universe such as ours. In this cyclical framework, collisions may occur again and again, giving rise to successive universes across unimaginable spans of time. The ekpyrotic vision reframes the Big Bang not as a moment of creation from nothing, but as the reverberation of higher dimensional dynamics, rippling far beyond the limits of ordinary perception. The holographic principle takes yet another path, dissolving our intuitive sense of reality itself. Inspired by black hole physics, it suggests that the entirety of our universe, the stars, galaxies, even the flow of time, could be a projection from information encoded on a distant, lower dimensional surface, just as a three-dimensional image can emerge from a two-dimensional hologram. So too could our universe arise from information written on the boundary of space. If this principle holds true, then the fabric of reality is not built from matter and energy alone, but from information, woven into the deepest architecture of existence. To live within such a universe is to dwell in a grand illusion consistent, tangible, and beautiful, yet at its core, an intricate pattern of encoded data. Roger Penrose's conformal cyclic cosmology takes a more philosophical turn, envisioning a cosmos with no beginning and no end. In this model, the universe moves through infinite cycles, but not in the form of expansions and contractions. Instead, the end of one universe, when all matter has decayed into pure radiation, becomes indistinguishable from the timeless conditions of a new beginning. The death of one cosmos folds seamlessly into the birth of another. In this picture, black holes evaporate, galaxies fade, and matter dissolves until only light remains. And in that ocean of radiation, scale loses all meaning. What was vast and ancient becomes indistinguishable from what is newborn. Time itself bends into a circle, each eon giving birth to the next, not through collapse, but through the sheer erasure of distinction between end and beginning, at the edge of speculation. Some theorists propose that time itself may be an illusion. In this radical view, what we experience as past, present, and future may not be a flow, but a fixed structure, a timeless block where every event, every birth, every death, every galaxy, and every thought already exists. The sensation of time moving would then be an emergent phenomenon, a property of consciousness navigating the frozen architecture of space-time. If true, then the question of before the Big Bang may be meaningless, for the universe is not a sequence unfolding, but a totality that simply is, eternal and complete. From here, the speculations only grow stranger. Some imagine that the pre-universe may have been a seething foam of quantum fluctuations, a restless froth where particles, energy, and even dimensions themselves flickered in and out of existence. From this chaotic sea, stability may have crystallized into space-time, igniting the cosmos as we know it. Others turn to the simulation hypothesis, proposing that reality itself could be the creation of a deeper intelligence, a computation running on an unfathomable substrate. In this vision, the laws of physics are the rules of a program, the constants of nature, the settings of an algorithm, and the cosmos itself a simulation real to those inside, but artificial to those who might exist beyond. Each of these ideas walks a fine line between science and philosophy, between daring imagination and unverifiable speculation. They remind us that the human drive to understand does not stop where evidence ends. It pushes further into landscapes where thought becomes as important as measurement. Yet through all their diversity, they share a common truth, that the universe resists finality, that the question of origins deepens with every attempt at an answer. Whether eternal inflation or holographic codes, whether colliding brains or cyclical eons, the search for beginnings becomes a mirror, reflecting both the cosmos and the limits of the human mind. Eternal inflation remains the most widely studied of these speculative frontiers, yet its implications are so vast that even within the scientific community it feels almost mythic. The mathematics of quantum fields interacting with gravity suggests that inflation is not something that must stop everywhere at once. Instead, it can slow and end in some regions, while persisting indefinitely in others. This means that the end of inflation is local, not universal. A single patch may cool into a universe like our own, while the surrounding expanse continues to inflate at speeds faster than light can traverse. Out of this eternally growing backdrop, new bubbles can form, each one ignited with its own Big Bang conditions. For observers within, each bubble becomes a universe complete in itself, yet forever isolated from its siblings by the relentless expansion between them. Such a picture suggests that creation is not rare, but common and ongoing process happening, without pause, filling the infinite void with an endless variety of realities. Some bubbles may collapse into sterile emptiness, others may thrive with galaxies and life, while still others may follow laws so alien that human imagination barely scratches their surface. the cosmic horizon we see in the night sky, so majestic and final, would in this view be only the wall of our own bubble, beyond which infinity still rages. If inflation proposes universes sprouting like seeds from a boundless field, the ekpyrotic model dares to place their origin in an unseen, higher-dimensional arena. String theory's mathematics provides a language for dimensions beyond the familiar three of space and one of time. Dimensions hidden but woven into the equations that describe fundamental particles. Within this framework, universes may take the form of brain's enormous membranes existing in higher dimensional space. The ekpyrotic hypothesis envisions our universe as one such brain, floating alongside another across an unseen fifth dimension. When these brains collide, their vast kinetic energy transforms into the heat and matter of a new universe. The shock of impact echoes as the Big Bang, not from nothing, but from the geometry of dimensions we cannot perceive. What is compelling is that this model naturally allows for repetition. Collisions may occur in cycles, separated by unfathomable spans of time, each collision birthing a new cosmos. In this way, the universe does not require a single beginning, but continues to arise from the endless dance of higher dimensional structures. The Big Bang ceases to be an origin point, and instead becomes an event in a larger drama, written on a canvas of invisible dimensions. The holographic principle, though born from black hole thermodynamics, extends its reach across all of existence. When Stephen Hawking and Jacob Bekenstein studied black holes, they discovered that the amount of information they could contain was proportional not to their volume, but to the area of their surface. This realization sparked a profound insight. Perhaps the same principle governs the universe itself. If the cosmos is a hologram, then everything within it, particles, galaxies, even the flow of time, is encoded on a distant two-dimensional boundary. What feels to us like depth and motion could be no more than an emergent illusion, a projection from information stored far away on the edges of space-time. In such a framework, the fabric of the cosmos is not matter or energy in its essence, but information itself, the same way a digital simulation arises from binary code. The holographic vision is radical because it questions not just the origin of the universe, but the nature of reality itself. If true, then the deepest mystery may not be how the universe began, but what kind of information it truly encodes, than who or what, if anything, reads it. Penrose's conformal cyclic cosmology brings a quieter, more philosophical elegance, while other models focus on dramatic beginnings or collisions. This framework suggests that the universe has neither a singular birth nor a final death. Instead, each universe, or eon, evolves until matter decays, black holes evaporate, and only radiation remains. In such a state, scale loses all physical meaning. Without masses or particles to measure time or distance, the universe becomes timeless, a sea of light without dimension. Remarkably, the mathematics of conformal geometry allows this empty, cold universe to be resculled into the conditions of a new Big Bang. The death of one eon becomes the birth of another. Time does not loop in a simple cycle of expansion and contraction, but flows through an infinite succession of eras, each one distinct, yet connected by the seamless transformation of endings into beginnings. In this view, the cosmic microwave background might even carry subtle imprints from previous eons' faint circles of radiation, echoes of black holes from universes long before our own. If such patterns exist, they would be whispers from a past beyond the Big Bang, woven into the very fabric of the sky. At the edge of these scientific landscapes lies the most unsettling possibility that time itself is not fundamental. According to certain approaches in quantum gravity, time may not exist as a fundamental dimension, but emerge only as an approximation from deeper, timeless laws. In these models, the equations describing the cosmos make no reference to a flowing present or a sequential past and future. Instead, they describe a totality, a static mathematical object from which the illusion of motion and change arises. Our perception of time, so immediate and inescapable, may be a feature of consciousness navigating a universe that in truth does not flow. If time is emergent, then asking what came before the Big Bang may be a misunderstanding. Like asking what lies north of the North Pole, the question itself dissolves, replaced by a vision of reality where the universe is not a story unfolding, but a timeless structure containing all stories at once. Still more radical are those ideas that slip across the boundary into philosophy. The concept of a primordial quantum foam suggests that before space-time itself crystallized, the universe may have been nothing more than a restless sea of fluctuations, where even the laws of physics were unstable. From this foam, space-time might have emerged in a process akin to crystallization, the way order can arise spontaneously from chaos. Others, inspired by technology, propose the simulation hypothesis that the universe itself is an artificial construct, the output of a computation running on an incomprehensible substrate. In this framework, the constants of nature are settings, the laws of physics are algorithms, and existence itself is code. The cosmic microwave background, the distribution of galaxies, the rules of quantum mechanics, these are the outputs of a program, meticulously computed. While unverifiable, this idea resonates with the holographic principle, for both suggest that reality may be far less material than it seems. What unites these speculations is not their certainty, but their daring. Each of them acknowledges the limits of present-day physics while refusing to surrender curiosity. They offer narratives that extend beyond the Big Bang, into realms of infinite creation, higher dimensions, eternal cycles, or realities built from information and illusion. They remind us that the question of origins may never find a single answer, but instead expand into a chorus of possibilities, each pointing toward truths just beyond our reach. In contemplating them, humanity engages in a profound act of imagination, escaping science, but extending it into the only terrain available when evidence runs thin, the landscape of thought itself. The story of the cosmos is not frozen in the past. It is alive, carried forward by instruments and minds striving to reach beyond the veil of the known, in deserts, mountaintops, and orbits high above Earth. Humanity has built machines that act as extensions of its own senses, probing deeper into the mystery of beginnings than any generation before. The universe may never surrender its secrets easily, yet today's frontier of science is an unfolding dialogue between human ingenuity and the silent depths of time. Each new telescope, each accelerator, each detector is an ear pressed closer to the fabric of reality, listening for whispers from the age before the dawn. Among these instruments, none looms larger in imagination than the James Webb Space Telescope. Suspended 1,000,000 miles from Earth in the cold shadow of the sun, it is less a telescope than a time machine. With mirrors gilded in gold and sensors chilled to near absolute zero, Webb peers into the faintest embers of the first galaxies. Its gaze stretches across 13 billion years, touching light born when the universe was less than 5% of its current age. Already it has uncovered galaxies that seem impossibly mature, vast collections of stars formed earlier than models had predicted. Their presence hints that the physics of the early universe may be richer, faster, and stranger than cosmologists once dared imagine. Webb does not simply refine the timeline, it challenges the very framework in which the timeline was written. Each deep field image is a reminder that the universe still has the power to surprise, reshaping our theories with every photon it delivers. Yet while telescopes search for the faintest glimmers, other efforts dive into the smaller scales of existence. The holy grail of modern physics is the unification of general relativity with quantum mechanics, a framework that could explain both the grand curvature of spacetime and the restless dance of subatomic particles. Research in quantum gravity seeks to weave them into a single tapestry. String theory, loop quantum gravity, causal dynamical triangulations, each offers a mathematical architecture where the Big Bang may not be a singularity at all, but a transition, a bridge, or an illusion, born of our limited equations. These theories suggest that what we call the origin may instead be a phase change, a crystallization from a quantum fabric more fundamental than space and time themselves. For now, the mathematics remain beyond the reach of direct verification, but they serve as lanterns, illuminating paths that future experiments may one day traverse to test such ideas. Physicists turn to colossal machines, particle accelerators, such as the Large Hadron Collider at CERN, recreate conditions reminiscent of the first trillionth of a second after the Big Bang. By smashing protons together at near light speeds, they momentarily restore energies not seen since the universe's infancy. The discovery of the Higgs boson revealed the mechanism by which particles gain mass, a cornerstone of the Standard Model, yet it also left gaps, questions about dark matter, dark energy, and forces that may exist beyond the known. Each collision is a probe into the hidden architecture of reality, a fleeting echo of creation itself. Plans for even larger collider circular machines spanning hundreds of kilometers promise to push further, perhaps uncovering particles that hint at entirely new realms of physics. Alongside experiments, vast computational simulations bring the early universe to life in ways no human eye has ever witnessed. Supercomputers now model the birth of galaxies, the cooling of primordial plasma, and the turbulent flow of dark matter shaping cosmic structure. These simulations are not idle exercises. They allow scientists to test the fingerprints of competing theories against the actual cosmos. By comparing simulated universes to the one we observe, researchers narrow the possibilities, discarding those visions that fail to reproduce the heavens. It is through these digital universes that humanity rehearses the origins of its own, refining hypotheses until they resonate with reality. At the edge of all these efforts stands a profound question. Is the mystery of before the Big Bang one that science can ever resolve? Some argue that it may remain forever hidden, shielded by horizons we cannot cross. Others believe that nature leaves traces, however faint, and that the right combination of mathematics, observation, and persistence will eventually uncover them. The James Webb Space Telescope, quantum gravity research, accelerators, simulations, and gravitational wave detectors are all threads in the same tapestry, woven by curiosity. Together, they form humanity's attempt to press against the final boundary, to transform the unknowable into the known. Whether the universe reveals its ultimate origin or holds it forever in silence, the pursuit itself stands as testament to a species unwilling to cease its questioning. For, in reaching toward the beginning, humanity finds not only the cosmos, but a reflection of its own unending desire to understand in the quiet stillness of night. When the stars emerge one by one and the weight of the sky presses gently upon the mind, a paradox takes shape. Human thought, restless and insatiable, asks what may be unanswerable, what came before the beginning. Yet the very word before dissolves under scrutiny, for if time itself began with the birth of the universe, then the question may carry no meaning beyond the frame of human language. Still, it lingers an echo that refuses to fade. This is the paradox of consciousness, to ask of realities it may never be equipped to know, to yearn for a horizon forever beyond its reach. Long before equations and telescopes, humanity sought origins in story. Ancient myths cast creation in the form of gods and battles, of cosmic eggs and endless oceans. In Babylon, the universe rose from the clash of primordial deities. In Hindu tradition, it emerged from the breath of Brahma, cycling endlessly through creation and dissolution. The Norse imagined fire and ice colliding to spark existence, while in the myths of the Maya, the gods fashioned humanity from corn and clay. Though diverse in imagery, each tale carried the same impulse, the same hunger to peer behind the curtain of the present and glimpse a first cause. Modern cosmology, with its inflationary fields, quantum vacua, and expanding space, may seem far removed from such mythologies, yet at its core lies the same yearning. Science, too, is a story told in the language of observation and mathematics, born of the same need to find meaning in the void. And yet there is weight in the realization that comprehension may have limits. The human brain evolved to track seasons, to read the intentions of others, to survive in landscapes of earth and water. It did not evolve to hold in mind the curvature of space-time or the foaming geometries of quantum gravity. To ask about a realm where even time may not exist is to stretch thought to breaking. Theories suggest that time could be emergent, not fundamental a property arising from deeper laws, like temperature emerging from countless atoms in motion. If so, then the arrow of before and after may be no more ultimate than the turning of a wheel. What lies beneath such emergence may not fit into the grammar of human thought at all. Here science finds itself humbled, standing at the edge of a great abyss of possibility. Perhaps some truths remain permanently beyond, not for lack of brilliance or persistence, but because the universe itself may not permit them to be grasped. There is dignity in such limits, as there is dignity in the silence of the stars. For in pressing against them, humanity learns not only of the cosmos, but of itself, of the courage to question, the humility to accept, and the wonder to continue. And so the meditation closes where it began, with the question of what came before the beginning. If time was born in the Big Bang, then there was no before, only the blossoming of space-time itself. To ask what preceded may be to peer into a mirror, catching a fleeting glimpse not of an answer, but of the edge of thought itself. In that edge lies a strange beauty, for it reveals that the act of questioning is itself a form of transcendence. The universe may not grant resolution, but in reaching for it, the human mind becomes a part of the mystery it seeks to understand, an echo in the dark, carried forward by the very flow of time it cannot escape. The paradox of asking what came before the beginning is not merely a scientific puzzle, it is a mirror held up to human thought, exposing the way language and logic strain under the weight of cosmic questions. Time, as lived by human beings, is simple. The rising of the sun, the flow of a river, the beating of a heart. Yet physics reveals time to be a malleable dimension, stretched and bent by gravity, slowed near black holes, and inseparable from the fabric of space itself. If this fabric had a birth, then so too did the very framework in which before and after exist. To ask what came before is to ask for shadows in a place where no light has yet fallen, and still thought insists on pressing against that boundary, as though silence itself demands a response. This tension between what can be known and what may remain forever hidden has haunted philosophy for millennia. Plato imagined that human beings perceive only shadows of deeper realities, while Kant argued that the human mind may never access the thing in itself, only the appearances filtered through space and time. In modern physics, this tension reappears in different form. If time is emergent, as some quantum gravity theories propose, then causality itself, the chain of reasons and consequences, may be secondary, not primary. What appears to human perception as a flowing river of time might be no more than the mind's interpretation of a deeper, timeless order. Some physicists speak of the block universe, where past, present, and future all coexist as a single four-dimensional whole, and the sensation of time's passage is a construct of consciousness. If this vision is true, then there was no beginning in the way the question assumes, only a vast structure of space-time existing as it is, eternal and complete. The question of before becomes a category error, like asking what lies north of the North Pole. Yet even in such models, the human imagination resists. It longs for a story, a genesis, a moment when the lights turned on. Here, ancient myth and modern cosmology converge once more. The mythic cycles of birth and rebirth, of fire and flood, of destruction and renewal, echo in today's theories of bouncing universes and conformal cycles. Roger Penrose's vision of a cosmos reborn from the fading ashes of black holes resembles, in strange poetic symmetry, the phoenix myths of old. The ekpyrotic model, with its colliding brains birthing fresh universes, mirrors ancient tales of cosmic struggle. Even the simulation hypothesis, radical and speculative, echoes mythic visions of worlds dreamed into being by higher intelligences. In each case, whether framed in religion, poetry, or physics, the impulse remains the same: to weave narrative where silence might otherwise reign. But there is another layer, motional rather than intellectual. To confront the limits of comprehension is to confront human finitude. The universe extends across scales so vast they collapse the ordinary measures of mind. Billions of years, trillions of stars, distances where light itself takes eons to arrive. And yet beyond this already incomprehensible immensity lies a deeper darkness, the possibility that even time itself may not be fundamental. To look upon this is to feel both wonder and vertigo, a strange mingling of awe and humility. The mind seeks ground and finds none. It grasps at the edges of thought and feels them dissolve. In that dissolution, some glimpse a kind of cosmic humility, an acceptance that perhaps not all questions are meant for answers. And yet, paradoxically, there is meaning in the very act of asking. To question what lies beyond the boundary of time is to step into a realm where science and philosophy merge, where imagination becomes as essential as calculation. It is a frontier, not only of knowledge, but of the human spirit. The telescope, the particle collider, the equations of quantum gravity are instruments through which humanity stretches its reach. But the question itself is also an instrument, one that shapes human identity. To wonder at what lies before beginnings is to declare that curiosity itself is limitless, even when the universe may not yield to it. Perhaps, then, the greatest revelation is not what is discovered, but what is revealed about the seekers themselves. Civilizations rise and fall, myths evolve into theories, and theories give way to new horizons. Yet the act of questioning endures, as constant as the stars overhead, whether the answer lies hidden forever or whether future generations will uncover truths now unimaginable. The pursuit defines humanity's place in the cosmos. It is not certainty, but wonder, that binds human beings to the universe they inhabit. In the end, the closing meditation returns to the edge where thought dissolves. If time began with the Big Bang, then the question of before may forever exceed the reach of words. And yet in asking, humanity touches the profound unawareness not of resolution, but of mystery itself. That mystery is not emptiness, but a horizon glowing faintly with possibility, calling the mind onward. For perhaps the edge of thought is not an ending, but another kind of beginning, the moment when the universe reflects back upon itself through the wonder of those who ask,